In non-relativistic quantum mechanics, the position vector x is the eigenvector of the position operator x cap, right? This is in non-relativistic quantum mechanics. Okay, in non-relativistic quantum mechanics, the position vector is the eigenvector of the position operator. So this is used to define the wave function. So the wave function is defined in non-relativistic quantum mechanics as psi of x is equal to x overlap with psi, and the amplitude mod psi of x square gives the probability of the particle at the location x. Okay, in Schrodinger picture, we start with a wave function psi of x at time t prime, and for example, if we want to find a wave function, the same wave function psi of x at a time t, right, then this will be the initial wave function and this will be the final wave function. So this is the question of quantum mechanics, that is, if you know the wave function at a time t prime, then you have to find the wave function at another time t. Now in Heisenberg picture, so this is in Schrodinger picture. In Heisenberg picture, the position operator depends on time. Okay, so x is x of t. Then the position eigenvector needs a time labeling. You cannot just write x, I have to write x t. Okay, so here xt does not mean that the state will evolve with time. No, that's not the meaning. The meaning is that we have an operator x which evolves in time, and corresponding state you have to label using time. So the corresponding state also needs a time labeling. Okay, so that is what I mean by x comma t. Now here the operator x acts on the state to give an eigenvalue and the eigenvector. Okay, so here the question of quantum mechanics is different. In Schrodinger picture, the question was, if I know the wave function at time t prime, then how do I find the wave function at a time t? But here the question is different. Suppose you are in an eigenstate, okay, at t prime with x prime, then what is the probability amplitude for you to go to a location x at time t, right? That is, I can represent this question by the overlap of x t x prime t prime is equal to, right? So here what is the question? Suppose you are in an eigenstate at time t prime, okay, with x prime, then what is the probability amplitude for you to go to a location x at time t? Okay, so this is given by a propagator g xt x prime t prime. So this is represented by g, which is called as the propagator. If you know the propagator of a quantum system, then you have full knowledge of the system and you have already solved that system, right? And if we want to find the wave function at time t, in Heisenberg picture, okay, then it is defined as x t psi. Okay, so from completeness relation, I can actually introduce something called as, okay, so x and t as it is. Now in between these two, I can introduce the completeness relation. So how do I do that? X prime, t prime, x prime, t prime. Okay, so I have inserted the completeness relation in between x and psi. Now if you see, this object is the propagator. So I can write integral d cube x prime g of x comma t, x prime, t prime. Then what is remaining? The remaining quantity is the wave function psi of t prime x prime. Okay, so if you want to find the wave function at time t, then I have to operate x with psi, and now I introduce the completeness relation. Okay, after incorporating the completeness relation, the first object is the propagator g, and the second object is the wave function at t prime x prime. So if you know this initial wave function psi of t prime x prime, and if you know the propagator, you just need to do an integral so that you get the final wave function. Okay, therefore the full knowledge of your quantum mechanical system encoded in the propagator g x comma t x prime t prime is equal to x t x prime t prime. Therefore this is a powerful object in non-relativistic quantum mechanics. Okay, so what we have seen is just the non-relativistic quantum mechanics. Okay, what is the analog of a propagator in quantum field theory, or how do we define a propagator in quantum field theory? To find this, we have to find the analog of position eigenstate in quantum field theory. In quantum field theory, there is no natural way to define a localized state such as x comma t, right? If you want to define propagator in quantum field theory, then you need a state xt in quantum field theory. But the problem is that in quantum field theory, there is no natural way to define localized state. Here, x is just a label and is no longer an operator. In quantum field theory, the field phi is the operator. Okay, in quantum field theory, field phi is the operator. Therefore, in quantum field theory, there is no position operator. There is no position operator. So there is no natural way to define the eigenvector associated with the localized state. So there is a problem here. There is a fundamental obstruction arising from the Lorentz symmetry. That is, we can show that a localized state in space is not Lorentz covariant. Suppose there exists some state x comma t. Okay, if suppose there exists a state x comma t such that x comma t overlap with x prime t is equal to the Dirac delta. So if you evaluate them at the same time, okay, then it will be proportional to delta function, because by definition what is meant by the localized state, localized at that point. Okay, so if you are evaluating the state at the same time, then it will be a Dirac delta function. If you can define such a state, then it is not covariant due to the presence of the delta function itself. Okay, so we have seen in the previous classes that if there is a Dirac delta, then it's not Lorentz invariant, it's not a good object. Then you have to multiply it with root of 2 omega so that it will become Lorentz invariant, right? So here such a state is not Lorentz invariant and it is not a good operator. So three-dimensional spatial delta function is not a good object in quantum field theory because it does not transform nicely under Lorentz transformation. If u lambda is the unitary operator that generates a Lorentz transformation, then you can show that this u lambda acting on the state xt is not equal to lambda x lambda t. The Lorentz transformation acting on x and t is not the same as the Lorentz transformation acting on x and the Lorentz transformation acting on t, right? This is not equal. Then the closest analog in quantum field theory, okay, so I need an eigenstate vector in quantum field theory, but that is not possible. But the closest analog in quantum field theory will be the object that is defined by x is equal to phi of x acting on the vacuum. Okay, so this is for a real field. Therefore, the operator phi will be Hermitian. So if I write, then the complex conjugate of the state vector x will be again phi of x itself, because this is for a real field. If it is a real field, then the operator phi will be Hermitian. Okay, since the vacuum is Lorentz invariant, okay, the vacuum is Lorentz invariant and the operator phi will transform smoothly under Lorentz transformation. The object x will transform nicely under Lorentz transformation. Therefore, I am defining x such that the operator phi acts on vacuum. So this can be considered as the closest analog of the position vector in quantum field theory. Okay. Therefore, if u lambda acts on x, you will get lambda x. Since the vacuum is also Lorentz invariant and the operator also transforms smoothly under Lorentz transformation, the object x will transform nicely under Lorentz transformation. Okay. Now consider the overlap between two such states. Then x prime will be equal to, by definition, what is x? Phi acting on vacuum. So this will be vacuum, phi acting on vacuum, x prime acting on vacuum. Okay, so this is the overlap between two such states. Now this cannot be equal to 0 for t equal to t prime and x not equal to x prime. Therefore, this object is not a localized state. this object is not localized. Therefore, this cannot be delta function. Now, given a single particle state psi, you can define its wave function in quantum field theory as psi of x is equal to the the state x overlap with psi, which is equal to phi of x acting on psi. Okay, so given a single particle state psi, you can define its wave function in quantum field theory as overlap with x. For example, if I take psi as a pure momentum state, okay, if psi is a pure momentum state, then this will be equal to k, which is root of 2 omega k vector k. Then the wave function will be, right, 0, phi of x and k, right, which is, so k is root 2 omega times vector k. So I can write root 2 omega 0 phi of x then k vector, right. Now what is k vector? K vector is ak dagger acting on the vacuum. So I can substitute here. This is equal to root of 2 omega k 0 phi of x. K vector is ak dagger acting on the vacuum state, right. Now here I have two operators, operator phi and operator a. So this is equal to root of 2 omega k. What is operator phi? Integral d cube k by 2 pi cube 1 by root of 2 omega k ak uk plus ak dagger uk star multiplied by ak dagger acting on the vacuum. Now root 2 omega k will get cancelled. I have vacuum, integral d cube k by 2 pi cube, then ak uk plus ak dagger uk star ak dagger acting on the vacuum. Now here I have to do cross multiplication, right. Integral d cube k by 2 pi cube ak dagger uk plus ak dagger uk star. Now ak dagger can be written as a commutator of ak and ak prime dagger plus ak prime dagger ak, right. So this can be replaced by the commutator, which is equal to 0 integral d cube k by 2 pi cube. Now I write ak prime dagger commutator plus ak prime dagger ak. Now this multiplied by uk plus ak dagger uk star, right? Now this acting on 0. Then I will get integral d cube k by 2 pi cube, expectation value of the commutator ak prime dagger, then plus expectation value of, and this multiplied by uk, okay, this multiplied by uk is also there, then this multiplied by uk. So ak dagger ak multiplied by uk plus last term is ak dagger uk star. So here if you see ak acting on 0 will be 0, so this entire term will be 0. And if you see here a dagger acting on 0 will be 0, therefore this is also 0. So I have only the first term, which is equal to integral d cube k by 2 pi cube, right? Expectation value of ak dagger ak prime dagger commutate, right? And this will be equal to 2 pi cube del cube of k, and this multiplied by uk is also there, so this multiplied by uk, k plus k dagger, right? So finally if you do this integration you will get just uk, because it's a Dirac delta function. Okay, so the wave function, so what we were finding is that the wave function, right, for a pure momentum state will be uk tx. Okay, so the wave function in quantum field theory will be e raised to minus I omega t plus I k dot x. So mod psi of x square in general cannot be interpreted as giving the probability of the particle at x. So psi of x is, so this is not probability. So psi of x is often used by the people and they just call it wave function. It is just a physical and mathematical analog of wave function in quantum field theory. Fine. Then in quantum field theory, the object g plus of x prime is equal to, I can define it in terms of the field phi of x prime. Okay, so here this is just a measure of the correlation between a physical object at different points. Okay, so this is just the measure of correlation between a physical object at different points. Okay, so here for x and x prime at non-equal time, phi of x and phi of x prime do not commute. So what happens is that the ordering is important in G plus. So G plus of x comma x prime, x comes first, x prime comes second, means phi of x will come first and phi of x prime should come second. The ordering is very important. Okay, so since phi and phi prime do not commute, then we can consider more general orderings, okay, including their superpositions also. So next I'll consider G minus. See, G minus of x prime. So if it is G minus, then I can write, so here x was first and x prime was second. Now I'm going to write phi of x prime first and phi of x next. Okay, so this is something like x prime x, and this will be x prime. Okay, so G plus and G minus, these two arises because phi and phi prime do not commute. Okay, so x and x prime at non-equal time. Therefore, the ordering is important, and we can consider more general ordering. So G plus and G minus is fine. Next, we can consider a retarded function GR. Okay, the retarded function x prime. Okay, so here I will use the function theta t minus t prime. Then I write commutator of phi of x, phi of x prime. So I can have many such orderings. So here I use the commutator. Here there is no commutator. So here there is phi of x prime, then phi of x prime, phi of x. But in GR, I am using commutator of phi of x and phi of x prime. Okay, so which means commutator in the sense phi of x prime minus phi of x prime, right, phi of x. So this is something like subtracting G plus and G minus. So this quantity I can also represent as delta. So I'll write delta of x prime. So commutator expectation can also be written as delta function. So I'll rewrite GR or the retarded function of x prime is equal to theta of t minus t prime. Then instead of the commutator, I can write delta x prime. This is the retarded function. Okay, and this theta of t minus t prime is equal to 0 if t is less than t prime. Okay, and it is the function theta of t minus t prime will take some value only if t greater than t prime. Okay, so this will take some value only if t greater than t prime, otherwise it is equal to 0 for t less than t prime. So that is the function theta of t minus t prime. So we have defined G plus, G minus. Okay, this G plus and G minus are also called as Whitmann function. The name is Whitmann function. And GR is the retarded function. Okay, retarded function. And next we can define advanced function. Advanced function, which is represented by GA x prime. Okay, this is advanced function. So here the difference is that you have a minus theta of t prime minus t. then this part is as usual. The spatial part is as usual. This is the advanced function. Next, I can also define a Feynman function. Feynman function, which I called GF of x prime. Okay, so this I can write as a superposition of g plus and g minus, that is theta t minus t prime multiplied by g plus of x prime plus theta of t prime minus t g minus of x prime. Okay, for the time being we define these objects just like this, and their meaning will be clear later. Okay, so I have defined g plus, g minus, gr, ga and gf. Now we will see the properties of these propagators of all these functions. The propagators g plus, g minus and delta satisfies the same equation of motion as the classical equation for phi. Okay, so this is only for g plus, g minus and the delta function, because they do not involve this term theta of t minus t prime. Okay, so g plus and delta do not involve this term, and therefore they satisfy the same equation of motion as that of the classical equation for the field phi, that is minus del square plus m square, phi is equal to 0. So similarly I can write del square plus m square g plus minus x prime is equal to 0, and del square m square then delta x prime. So both g plus minus and delta obeys the classical equations for phi, whereas ga, gr, gf, the advanced, retarded and the Feynman functions, okay, they do not obey the classical equations of phi. They obey something called as del square plus m square, right? G, it can be retarded or advanced or Feynman. Okay, they all leads to the delta function, 4-dimensional delta function. It's not 3-dimensional, it is 4-dimensional. Okay, so this is a 4-dimensional delta function both in space and time. Okay, whereas GRAF obeys this, which is a 4-dimensional delta function. Why it is a 4-dimension? Because it is both space and time. Okay, the partial square here contains time derivatives, and when you add the time derivatives or operate these time derivative on the theta functions, okay, so g, r, g, a and gf, they all contain theta functions. So when these time derivatives present in the del square act on the theta function, they give delta function. So that's how you get a separate equation for gr, ga and gf, but g plus minus and delta function obeys the usual classical equations of phi. So that is the first property. Now phi of x prime, we have seen that in general they don't commute at unequal times. Equal times they commute, but now we are considering unequal times. So phi of x and phi of x prime in general do not commute at unequal times, but for space like separations, So what is space like? Space like means x minus x prime whole square is greater than 0. Okay, so there is time like, space like, and light like. So here what I am going to say is that phi of x and phi of x prime in general they don't commute. Don't commute at unequal time. But for space like separations, that is for x minus x prime whole square greater than 0, what happens? They commute. Phi of x and phi of x prime commutator is equal to 0. So this is a special case. So how do you derive this, or how do you explain that for a space like separation they commute? So for that, let take the deviation delta x prime, okay, is equal to, so here I am not taking the expectation value. Okay, so delta means there will be an expectation value. We have defined like that, right? So if you see here, there is an expectation value and the commutator together, which we called as the delta function. So there is no cap here, it's just delta. It's not delta cap because it's not an operator. Okay, why it is delta? Because there is a expectation value here, 0 and 0. Okay, but if I am not writing those expectation value, then if I am not writing this, then it has to be delta cap. So I am not writing the expectation value. Okay, so this is an operator, so I can represent this operator by just the commutator phi of x, phi of x prime. Okay, so if you look at the commutator between phi and phi prime, there is always a commutator between a and a dagger, right? Because phi of x contains a plus a dagger, it is of that form, and phi of x prime will also of the form a and a dagger form. Okay, therefore their commutator will also be a constant because a and a dagger will give a constant, right? Therefore this commutator value will always be a constant. Otherwise I can write it is a C number, constant number. So it can be real or complex, but it is a constant number. Now the Lorentz transformation is defined by u lambda is equal to e raised to I omega mu nu m mu nu, right? So by definition, if the Lorentz transformation acts on phi of x, right, then I get phi prime of x. But the Lorentz transformation actually acts on the space, therefore this is phi of lambda inverse x. This is by definition. Now let's operate the deviation with u lambda, that is u lambda acting on the deviation, right? Then what is happen? I can substitute for deviation. So u lambda deviation means it's phi of x prime. Then u lambda dagger. But we know that this is a constant or a C number, right? The deviation is a constant. Therefore it will be u lambda some constant u lambda dagger. So this will be u lambda. This is on the left hand side. Now on the right hand side, u lambda acting on phi of x, right? So this will give you the transformation, Lorentz transformation. So I can write phi of, so this is the Lorentz transformation. Here it will be x prime. So u lambda acting on a constant will be constant. So here you have a constant equal to, so what is this? This is again a deviation, right? Deviation between this and this. So you can see that this deviation is also a constant. So when we make a Lorentz transformation on the deviation, actually nothing changes. It's just the constant. See, this is also a constant. See, you get the same constant after the transformation also, right? Even after the transformation, there is nothing that is changing. So when we make a Lorentz transformation on the deviation delta, actually nothing changes and the value is the same. For any space like separated x and x prime, we can always find some lambda such that if lambda is acting on x, then you get a time and x can become y. Now if it acts on x prime, then t tilde y prime. Okay, so for any space like separation x and x prime, okay, space like in the sense x minus x prime whole square is greater than 0. So for any space like separation x and x prime, you can always find a lambda such that the transformation remain at equal time. So some Lorentz transformation. What do I mean by this transformation? See, in both the transformation you can see that time is equal. So there exists some Lorentz transformation at equal time. Okay, then we find if it is an equal time, then what happens? The deviation x prime will be 0. There will not be any deviation. Why? Because what is this deviation? It is the commutator of phi of x and phi of x prime. If it is at equal time, then they commute each other. Therefore, the deviation will be 0. Okay. So this is equal to 0 because the commutator is evaluated at equal time. So this is very intuitive, okay, but it is a precise proof for the statement. So what was our statement? Phi of x prime in general do not commute at unequal times, but for space like separations they do commute. So we have proved that there can exist a Lorentz transformation at equal time, right? The second property also shows that, okay, when we talk about canonical quantization, we need to impose equal time commutator to be 0. Now we can see that this does not break Lorentz symmetry, because if you have only space like separation, even then the commutator is always the same. So no matter what frame you choose, if it's equal time and it's always space like separated in some other frame, okay. So for space like, the essence is that for space like separated x and x prime, g plus will be equal to g minus equal to gf. Why? Because time ordering does not matter. What is the difference between g plus and g minus? In g plus, phi comes first, then comes phi prime. In g minus, phi prime comes first and then phi comes, right? That's why we defined g plus and g minus. But for space like separated x and x prime, g plus is equal to g minus is equal to gf implies time ordering does not matter. Okay, this is for space like separated. And also gr is equal to GA is equal to the deviation is equal to 0. Okay, because we have already proved deviation is 0. If deviation is 0, then GR and GA must be 0 because they contain the deviation, right? Yeah. So this is the second property. The third property says that due to space-time translation and Lorentz symmetries of the vacuum, then any of the functions g x x prime. So here I represent g x x prime. This g can be any g. Okay, so any of the functions g can be expressed as, that is g of x minus x prime, which is g of x minus x prime whole square. That is the functions, any of the functions g depend on the 4 distance between them. Okay, so x and x prime are having 4 components. X has 4 components, right? X prime also has 4 components. Therefore, naively we expect g to have 8 variables. Okay, so this third property says that under the symmetry, under some symmetry, here what it says is space-time translation and Lorentz symmetry. Under some symmetries, g is a function of only a single variable. What is that single variable? That is the distance between the 2 points. So whenever you have a translational symmetry, the choice of reference point does not matter. Okay, only the separation between x and x prime matters. So x can be at origin, x prime can be at some other point. Okay, x can be at any point, that does not matter. Only the separation between x and x prime is what matters. So this is always true, but only in the vacuum state, which has the property space-time translation and Lorentz symmetries. Okay, so vacuum state is invariant under the above transformations. So this is true for the vacuum state. So today's class we will stop here and we'll continue in the next lectures.